Welcome to the physical science virtual session number 2. We are going to be taking notes together on a lesson that most of us have not done yet. I'm hoping, because it's due later this week for you. So we'll start here with a little PowerPoint. All right, we're going to be talking about acids and bases in this lesson, and we're going to go through the Canvas lesson together. I already took notes on it, so we're going to go through, and I'm just going to show you a way to take notes, right? The hard thing about notes is that there's not really a right way. Some people can write down 4 sentences, and that's all they need, right? Some people need to write more than that. But there is kind of a wrong way to take notes where sometimes people will write every single word down, or they're not summarizing or picking out the important information, which is an important step in the learning process. If you can take a paragraph and put it into one sentence, right, that means you really understood what you were reading and you weren't just copying word for word what you see. You could barely hear me. Is that better? That's surprising, Alina, because you know I'm really loud. So try your speakers. Can everyone else hear me okay?
Yeah, I can hear you.
Okay. Yeah, Alina, try just turning your speakers up. It might just be you. Or Elizabeth says log out, log back in. Okay. I was going to say, I'm really loud, and I have my volume all the way up. Okay. All right. So what we're going to do is we're going to compare acids and bases and their properties. A lot of that might be review. We're going to relate pH to the hydronium and hydroxide concentrations. That might be new. We're going to calculate the pH using molarity. I always get mortality, morality, and molarity confused. Molarity of hydrogen ions. And we're going to model note-taking, right? As I said, one method. So this third bullet point, this is going to be a pretty new thing. They kind of touch it on it in the lesson, but they explain it really badly, so I'm going to explain it better, and then you guys will be able to calculate the pH. So acids and bases, right? Just a little bit of background about them before we get started here. Arguably, this is the backbone of chemistry, right? A lot of stuff involves acids and bases and the reactions that they have together. In fact, there's a whole section of chemistry called titration, where you're just mixing acids and bases and trying to make them neutral. And it's really hard, actually. They're used in your everyday life, right? Including in your body. Your blood has a pH of 7.4, right? So your blood is slightly basic, and that's a super important number. If it varies just even the tiniest bit, you could die, right? So your body is constantly working to maintain that pH. And they're pretty much direct opposites. As we'll observe in the properties, you can think of them like opposites, and when they come together, they cancel each other out, basically. So, notes. I have a document camera, which I'm pretty excited about. And hopefully you guys are going to be able to see this pretty well. It's going to be a little confusing because I'm also going to refer to the Canvas lesson, which... Come on, go away, little bar thing. I never realized either that you guys can't see the little bar. This, like, every time I try to go to the top of my browser, the Canvas, like, bar comes down and I can't click on anything, and it irritates me so much. And I saw in somebody else's virtual session that you guys can't even see that. So I just look like I can't use the computer, but I promise it's there and it's annoying. All right, so when we first open this Canvas lesson, we're going to see this little activity here where you can dip your pH paper, or you have to pick up the pH paper possibly. There it is. You can pick up your pH paper and you can test a bunch of substances, right? And you can compare them over here. So vinegar is in the 2 to 4 pH range. Deodorant, also in the 2 to 4 pH range. Window cleaner, 11 to 4, right? You can go back and try all of these if you'd like. Water is a nice, beautiful 7. But basically, this is actually how you would do this in a lab. They have this paper called pH paper that can turn colors based on what pH it is. And we'll do that in the next lab that we have, which isn't for a while, but we will do something with pH. So the most important part of this first page is always the objectives, right? Which I know most of you guys probably skip over and don't even look at, which I don't blame you. But they're important because that's what you should be getting out of the lesson. And if you go through the whole lesson and you can't do those things, right, that means you need to go back and find them. The first one is going to be compare acids and bases and their properties. So we're actually going to ask ourselves at the end of this lesson, can we do that, right? The second thing is relate the pH of the solution to its hydronium and hydroxyl ion concentrations and its acidity or basicity. Ugh. Hard words today. So we want to make sure we can do both of those things. All right, so the beef of the lesson here is on page 2. And so I have already wrote quite a bit of stuff. I did add some extra stuff as well. So I'm going to move this thing over here. Okay. Let's see, we'll do it this way. Should be good. So this is how I started off my page. I wrote the date, I wrote physical science, acids and bases, that's what the lesson's called. And I wrote the objectives. You don't have to write them, right? But I thought it would be nice so that when I'm studying and reviewing, I can see what did I need to know about acids and bases, right? What kinds of questions are they going to ask me? So first part of this lesson here is about acids, right? And they have 3 things. They have just general, like a definition of acids. They have its composition and formula, and then properties of acids. So that's how I divided up my notes here. I started off with the definition. So the definition of an acid, right? They give us this long, long paragraph. So I'm going to read it to you, and I want you to be thinking, how would you summarize this into 1 sentence, or at least 2 sentences? Chemically speaking, an acid is a compound that increases the concentration of hydrogen ions when dissolved in water. A hydrogen atom is a proton and an electron. When it loses the electron, it is just a proton. Hydrogen ions are protons, but they do not remain alone in water. They chemically bond to water to form H3O+ or hydronium ions. For all intents and purposes, H+ and H3O+ mean the same thing. They both refer to positively charged hydrogen. Then they say, watch how hydrogen acid or hydrochloric acid separates when it is added to water, which we'll watch in a second. So hopefully you were thinking about summarizing that in your mind, but all of that text, all I wrote was compound that increases H+ or H3O+, and then I wrote out the word hydronium ions, right? That's all it does. And they're right. For the most part, chemists consider H+ and H3O+ to be the same. They are slightly different, mostly because H+ would never exist by itself. A lot of times we just call it H+ just because it's easier. Okay, so we'll watch this little video here.
This is also an experiment you can do at home. What you need is you need a small container that's going to have some water. We are using hydrochloric acid, but you can do your experiment using vinegar. We have pH paper that you can find. If you look in your phone book, you can find a school supply store. Also, some of the hobby stores are going to carry it. We also have a set of tongs, but you can also use tweezers. The first thing we're going to do is we're going to test the pH of our water. I'm going to dip the pH paper in and compare it to the scale that came with the pH paper. Notice that our color is not quite as dark as the pH of 8. It also is not the color of the pH of 6. So it's somewhere in the middle, and this would be a pH of 7, which means that it's neutral.
By the way, this is not the best quality video of all time. 1, what is this music? And 2, right? This lady is taking way too long to explain this, but we're not going to watch the base one, but we'll watch this one.
We're now going to take another piece and we're going to just test the pH of our acid. I'm going to dip this in. If I look up here, it's about the color that is at the top, and that says pH 2, a strong acid. And hydrochloric acid is like what's in your stomach. Now, when we add the acid to the water, the acid actually breaks apart to form hydrogen ions, which are H+, and chloride ions, which are Cl-. The hydrogen ions are going to then react with the water to form a hydronium ion, H3O+. It is the H3O+ that makes this an acid. So I'm going to take my pH paper again, and I'm going to dip it in the water and see what happens. Notice that here is my original water, which is a very, very pale yellow. Here's my hydrochloric acid, this nice bright pinkish purple. And here we have the acid with the water. Notice that when we added the acid to the water, we got a pH that is between 7, the neutral for the acid, and 2, which is our pure acid. When you get your pH...
Okay, so basically all she's saying is if we add acid to water, we make the pH more acidic, which should not surprise us at all, right? So now we're going to talk about acid composition and formulas, right? So this is where it gets kind of complicated because there's actually a lot of rules for how to say different compounds in chemistry, but then there's also about 45 exceptions to the rule. I think more than that, probably like 4,000 exceptions. So when you take chemistry, you're going to learn all that fun stuff. But for the most part, acids do contain a hydrogen, right? They don't all contain a hydrogen, but most of them do because we need the hydrogen to break off, right, and form those H+ ions or form those H3O+ ions. So here they're saying that exact thing. There are some exceptions, right? Carbon dioxide and sulfur oxide, I believe is how you say that one. They create carbonic acid and sulfuric acid in water, right? But they don't have an H in their formula. So it doesn't have to have an H to be an acid. So here are some pretty commonly used or found acids here. I'm going to show you guys my notes page now. I'm super proud of it. I use like 4 colors. It's exciting. Okay. I tried to make it exciting. So for the formula and composition, I wrote all acids contain hydrogen. There's exceptions, right? Carbon dioxide, sulfur oxide. They react with water to increase the hydrogen ions, but they don't necessarily contain hydrogen ions. Then I wrote some examples here. We have the phosphoric acid, nitric acid, hydrofluoric acid, and hydrochloric acid, right? They explain what those things do. Phosphoric acid is what's found in sodas. Nitric acid is in fertilizers. Hydrofluoric acid is used to clean metals. And hydrochloric acid, which is what she was using in the video, it's probably like the most famous acid, I would say, right? That's actually your stomach acid for the most part. And it's a really strong acid. And if you get it in a super pure form, it can burn through your skin, which is scary. And then I also wrote this tiny, tiny thing. I don't even know if you guys can see this. I kind of made an error here because I balanced the equation. I'm going to fix that. Plus 3Cl minus. So basically what's happening when you add this hydrochloric acid to water is we're starting with hydrochloric acid and water. We get hydronium ions, H3O+, we get chlorine ions, and we get water, right? And then these hydronium ions, this is what makes it acidic. So when we add that HCl into the water, right, those hydronium ions increase, and that makes the water's pH become more acidic. I just balanced the equation here because you would need to add 3 HCl molecules to 1 water molecule in order to get that separation. So, properties of acids. Now, this is always the part that worries me because all these properties involve like touching and tasting acids, which you should never do because they could kill you. But they supposedly taste sour. Right now, we do eat some acids, so that's fine, right? Like lemons are acidic, they're sour. Acids are corrosive, right? If you think even about soda, if you've ever poured soda on like a car battery or any kind of battery, it will clean off the battery acid, which is disturbing because you're putting that in your stomach. They all increase the hydrogen ions, right? We could also even say, or the hydronium, what's the word I'm looking for? The hydronium ions. They form hydrogen gas, right? I put a little tiny G next to it because that in chemistry is how we denote the phase when mixed with a metal, right? So if you pour an acid on a metal, it will release hydrogen gas. And an acid plus a base, if you add them together, is always going to equal a salt and a water, which is pretty cool because that's a really great way where if you spill an acid that's super dangerous, assuming that it's not burning through the floor, which could happen, you can pour a base on it, right, and neutralize it, and then it'll become water, and then you could just stick your hand in it and you would be fine. Would not recommend trying that at home, but you can do that. So that's a good thing to know, right? They do cancel each other out. Now, another interesting thing that they don't mention in this lesson that I thought was important to mention here is that water by itself ionizes. So when you have multiple molecules of water together, they ionize the water molecules to get a hydronium and a hydroxide, which we're about to learn is for a base. So water does that on its own. Now, the reason there's 2 arrows here, right, there's an arrow going right and an arrow going left, is because this is happening both ways, right? So the water is not ionizing and staying ionized. It's ionizing and then going back to water, and then ionizing and then going back to water. And it's just continuing to switch between the 2. Now, there's different pressures and temperatures, et cetera, where this happens more often than usual, right? But we don't really need to know that. I just wanted you to understand here that water ionizes on its own, right? So when you're adding these acids, it's just increasing that ionization process. Okay. Do we have any questions so far? Okay, are we all falling asleep so far? I should be, okay, you know what we'll do? Type 1 in the chat if you're still with us. Okay. Yay! Okay, people are with us. All right, good. I'm trying to make this interesting, guys, but I'm trying to make it useful because if you haven't done this lesson yet, guess what? Now you don't have to do it on your own. All right, we're going to move on to bases now, which, as we can imagine, are basically the opposite of acids. Same exact setup here. We're going to do the definition, the properties, and the composition and formulas. And for some reason, they didn't make a little box. Like for this one, they made a little tabbed box. For bases, they didn't do that. Not sure why. We're not going to watch that lady's video because it's the same thing, basically. But we will quickly go through this. So a base is a compound that increases the concentration of hydroxide ions, or OH negative ions, when dissolved in water, right? They say watch the video to see how it happens. We can imagine in our minds, it's going to look like water, and it's going to have a different pH. So when we look at what I've written down so far, right? Definition: increases the concentration of OH hydroxide ions when dissolved in water. Okay. Most bases do contain OH ions in them, right? They're called aluminum hydroxide, for example, sodium hydroxide, etc. they contain the hydroxide in them for the most part. There are exceptions. And when we see a base in water, right, it's just going to separate out into ions. We have sodium ions, we have hydroxide ions, and we have water. Those hydroxide ions, that is what makes this a basic solution, right? The more OH ions you have, the more basic your solution is going to get, which sounds kind of funny, but examples of bases, right? They have them here as well. We have aluminum hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide. I didn't even bother to write the names of them because they're all basically the element plus hydroxide. Now, we're going to make this a little more complicated. So I drew here what the chemical structure would look like for calcium hydroxide, right? Because I was hoping that people would be thinking, well, how come there's 2 hydroxides with calcium, but there's only 1 with sodium or only 1 with potassium, right? And this is going to connect us back to the periodic table, which is why you start learning about the periodic table before you get into this. So calcium, right, if we look at a periodic table, which I probably should have pulled one of those up. All right, if we look at a periodic table of elements, we see calcium is in the second row, which means how many valence electrons does calcium have? And then Elizabeth, I'll get your question. When will this be over? Thanks, Alina. It's probably going to be over in about 20 minutes. 2, right? Calcium has 2 valence electrons. If you haven't learned about that yet, you'll learn about it hopefully soon, right? But we have 1 valence electron, 2 valence electrons, then we jump across the transition metals because they're very weird. 3, 4, 5, 6, 7. So calcium has 2 electrons that it can donate. That's why when we see this bonding between calcium and hydroxide ions, right, we know oxygen has 6 electrons. It needs 2. Calcium can give up 2 electrons. Hydrogen can give up 1 electron, right? So the oxygen ends up bonding with a hydrogen and a calcium, which will give the oxygen 8 electrons, right? And then we have the same situation happening on the opposite side. You could draw out the electrons here, where we have 1 electron with calcium, 1 electron with the hydrogen, and then the oxygen already has 1, 2, 3, 4, 5, 6 that it came with, right? So oxygen now has a full set. And everybody's happy, right? So I challenge you to think about why aluminum, sodium, and potassium are different, right? Again, going back to those valence electrons. Potassium and sodium only have 1 valence electron. Aluminum has 3, right? So that actually is why there's different numbers of hydroxides. All right, Elizabeth. Oh, okay, Alina, thank you. If you need to leave, you can leave. This is recorded, right? So you can always come back. Elizabeth, that is a great question. How do scientists know if acids and bases taste sour or bitter? Yeah, so in some cases, right, we eat or can eat those bases and acids. So for example, soap, right? Soap is a base. Now, would you want to eat soap? Probably not. When I was little and I was I was a really bad child. I talked back to my mom a lot. She used to wash my mouth out with soap. So I'm very familiar with the taste of soap. It tastes super bitter and disgusting, right? Same with lemons. Lemons are acidic. They taste super sour. Now, for the most part, I'll give you the soap. Once we get to a certain pH, right, I'm hoping that no one has tried to taste those things. Bases also feel slippery, right? If you think about like a lemon, if you touch lemon juice, right, it kind of burns you a little maybe, but it's not slippery. If you touch soap, it's super slippery, right? You're dropping it, it's flying everywhere, it's sliding. So they kind of made those generalizations based on the bases and acids that we can touch and eat. I'm sure that there were people who, you know, back when we didn't really know much about chemicals, didn't know much about hydrochloric acid, I'm sure that there were chemists that did touch it and had it burned through their finger. Hopefully they didn't taste it. Also, you can, if you breathe in the fumes of acids, you get this weird sour taste in your mouth. When you're in a chemistry lab for like 4 or 5 hours and there's lots of acids and people are using them, you end up like breathing in that fume, and yeah, you get this weird taste in your throat. Hard to explain, but one day maybe you'll experience it. Definitely not desirable. But yeah, so I think really the way that they figured that out was just by using the pH of the acids and bases that we actually can touch and taste. But it is a good question, right? Because if you think about it, now that we know so much about chemistry, it's not that scary. If something is scary, people are like, oh, don't touch that. And you're like, all right, I don't want to burn my hand off. Back in the day, no one really knew what was going on. They were just touching, tasting, doing whatever. And, you know, they didn't realize maybe that some of that stuff could actually burn through you, right? Because humans always think, oh, yeah, that's not going to hurt me. It can. And it's scary. So, and also chemists didn't know about cancer-causing agents, right? Carcinogens. So a lot of the stuff that they were touching and using that wasn't actually dangerous in terms of being an acid or a base was a carcinogen and actually caused them to get cancer. So being a chemist is pretty intense. Mostly because the labs take a really long time. Ugh. Okay. So that's what we have so far for these bases. We will now go back. All right. So then they also talk about the properties, right, which a lot of us already know the properties or we've heard of them before. Bases are bitter. They're slippery. They have a high amount of OH ions. And then again, an acid plus a base equals a salt plus water. So here I actually give you an example of that. Sodium hydroxide, a base, hydrochloric acid. If we mix them together, right, in equal amounts, we will get NaCl, which is table salt, and water. Would you want to touch hydrochloric acid or sodium hydroxide on its own? Definitely not. Could you touch water and salt? You could, right? So that's actually what happens. Now, if you add more sodium hydroxide than you add hydrochloric acid, you will still have a base, right? You will still have hydroxide ions floating around in that water, and it could still be a basic solution. So it's only when they're in equal amounts that you're going to get 100% water, 100% salt. So that's important to think about. Okay. By the way, I'm going to post pictures of these notes. So if I'm going too fast or you want to look at them later, I don't know what to cover up here. I guess we'll do it like this. Okay. So next they go into the pH scale, right? Which most of us are already kind of familiar with what the pH scale is, right? It's a scale that shows us acids and bases. The weird thing about it is that neutral is in the middle, right? Neutral substances are found in the center of the pH scale rather than on the left or the right. So as we go to the left, we go down in numbers, we get the strongest acids. In fact, the scale actually technically does go to 0, which is the kind of acid that burns through your hand. We also go all the way to the right. We increase in numbers. We end up getting really strong base, right, at 14. 14 is the highest number. And again, those bases could burn through your skin. Like bleach is, I believe, a pH of 13, not even a 14. I don't know if you've ever gotten a burn from bleach, but it hurts. Okay, so what I've done here, based on what they had in the lesson, is I just wrote out the concentrations of hydroxide and hydronium ions. So I did hydroniums in purple. So what we notice is that the strongest acid, the concentration of hydronium is 1 times 10 to the 0, which is just 1. That means that the highest concentration of hydronium is 1, right? And then we go down. We get 1 times 10 to the negative 1, which I didn't write because I didn't have enough space. 1 times 10 to the negative 2, 1 times 10 to the negative 3, 1 times 10 to the negative 4, right? That one's pretty easy to do for the hydronium concentration because it goes with the numbers. You're basically just going to have 1 times 10 to the negative whatever number you have. The hydroxide ions, on the other hand, right, the OH minuses are going to be the opposite. 0 is going to start over here at 14, and we're going to go -1, -2, -3, -4, all the way to -14. So we'll talk about what that means in a second, but something important to note is that at a pH of 7, which is a neutral pH, we have an equal amount of hydrogen and hydroxide ions, right? They're both 1 times 10 to the negative 7. At that point, that's a neutral solution. Let's look at the numbers, what these things actually mean. So you can't really tell in here because I tried to write my zeros nice and evenly, but I didn't. The top one has 12 zeros, the bottom one has 11 zeros, right? I did 1 times 10 to the negative 13, which remember means you put the decimal place after the 1, and then you move it over 13 places. So we're going to get a pretty tiny number here. We have 12 zeros and then a 1. 1 times 10 to the negative 12, we actually have 11 zeros and then a 1. What that means is that going from a pH of 12 to a pH of 13 is 10 times stronger. 10 times stronger. All right, I have to use the bathroom, which is strange. I'm gonna leave this for a second. I want you to think about that. If it's 10 times stronger, why is that a big deal? When I come back, I'm gonna hope that at least 2 people can tell me that. Why is something being 10 times stronger a big deal? Okay, I'm back. I drank a lot of coffee today so far. Okay, so because it's over 9,000, yeah, so if each time we're getting 10 times stronger, right, then the difference between 0 and 2 is actually 100 times, right? And that should be intense to you because usually when we look at something on a scale like this, going from 0 to 1, it's just getting 1 times bigger, right? Going from 0 to 2 would be 2 times bigger. In this case, we're doing in a base 10 logarithm, actually. I know, don't worry, we're about to get into the math. Where it actually is increasing by 10 times every time you go up or down a number, right? Or it's decreasing by 10 if you're going down. So that means that we're talking about a huge difference between something that's a pH of 8 and a pH of 9, right? It's not just a tiny change. It's a big difference. And Zach's right. That makes this an exponential relationship instead of a linear relationship, which is exactly true, right? They're not increasing at the same rate here. And so the reason that that matters here is, like, for example, in your body, your pH is 7.4, right? If your pH goes down to 7.1, you die. What? That's like barely any change. But because it's an exponential change, right, it's a lot more than just going down 0.3. So in that case, hopefully that helps you think about this a little bit, right? A tiny change here in the pH could really change a lot of things, especially when we think about living things, right? Like the pH of water is super important. Same even with the pH of pools, just for our own fun, right? We want our pH to be accurate so that we're making sure we're killing germs, but also it's not so strong that it's hurting us, right? Like you've probably been in some of those pools that have too much chlorine, right? And you're just like, you could feel it like burning you, right? That's not what anyone wants. Okay, so then the last thing that we're going to talk about here is molarity. So they give us this little thing to play with, which we don't need to do, but measuring concentrations. So molarity is one way of measuring the concentration of a solution. We abbreviate it with a capital M, right? That stands for molarity. And 1 mole is actually equal to 6.02 times 10 to the 23rd, right? It's something called Avogadro's number. You'll learn about it when you take chemistry. But basically 1 mole is 6.02 times 10 to the 23 ions of something, right? And for the most part, we don't really care because when we're talking about pH, we're just going to be looking at moles. We're not going to be looking at changing it back to ions and whatnot. But just keep that in your mind. When we're saying something has 1 mole, we're saying that it has 6.2 times 10 to the 23, which again, remember, that means we're moving the decimal to the right 23 times. So that's a lot. So they show this how to calculate molarity thing, which doesn't make any sense to me. When I read it, I was like, what are they talking about? Which thankfully I knew how to do it. So I'm going to show you how to do it. So don't look at that because, what is that? By the way, if that ever happens where you're like, what do they mean? Try Googling it. I guarantee you there is a YouTube video or some kind of chemistry website that will show you how to do it. So this is where the math comes in, how to calculate pH. So pH actually has a nice formula using logarithms, everyone's favorite mathematical representation. And the good news is we're not going to be having to convert these logarithms. They're all base 10 logs, which means we can use a calculator. And should be pretty simple. It's basically a plug and chug type situation, as we say in math. So if we want to find the let's see. So pH actually equals the negative log of the concentration of hydronium ions, right? And this is in moles, or the capital M units. So an example, find the pH of a 0.0025 molar hydrochloric acid solution. Hydrochloric acid is 100% ionized in water, right? They tell us that because I took this example from a really legitimate chemistry website. Some acids don't dissolve completely. They don't ionize completely in water. And that would make your math much harder, right? Because if it only is ionizing a certain amount, then that's going to change how you do this. That's going to be something that you learn later on. We're doing the basics here. All we do is plug in. pH equals negative log. We plug in our concentration, 0.0025. We calculate that, the log of 0.0025. And we get negative 2.602. We can just round it to negative 2.60. We have a negative of a negative, right, which just becomes a positive number. And we end up getting that our pH is 2.6. Now, pH doesn't really have units, which is kind of weird, right? The units are implied, I guess, is kind of how it works out. So pH is the only time really where you can just write 2.6 and you're done. So that doesn't seem too hard, right? Something else we can do is if we want to know the concentration of the hydroxide ions, which we call the POH, we can use this little fun fact here that the pH plus the POH is equal to 14. So taking that number that we just found, right, if our pH equals 2.6, and we want to find out what our pOH is, we're just going to plug in what we know, 2.6 plus our pOH equals 14. We're going to subtract 2.6, right? And then that's how we find it. So really not too hard. You can use a calculator to do this, right? They're not even really going to ask you to, hold on, I got to do this in my head. 11.4. Okay. They're not even going to ask you to do this necessarily in the course, but I think it's important, right? Because when you get to chemistry, you're going to do a lot of this, and it's going to get more complicated. So we can find our pOH concentration just by simply subtracting. Okay. Now we will try a few more examples. You guys are going to try. Okay. So pH practice, actually, I'll leave this. Oh no, my computer's going to sleep. Okay. So, come on, George. I want you guys to try these, right? Remembering the formula is, hopefully you wrote it down, pH equals the negative log of the hydrogen concentrations. So I will give you, we'll do like 3 minutes here, and then I'm gonna do the first two, and then assuming that you got those two, you'll get the last one too. So take a couple of minutes here, try to solve those. You can even type log into Google, and I'm pretty sure you can find the log of stuff there if you don't have a calculator. Okay, so hopefully you at least got to try the first one, possibly also the second and third one. I have worked out what I got. Actually, you guys tell me, what did we get for the first one? If we're trying to find the pH, we have a hydrogen concentration of 0.007. There's 7 zeros. What did we get? Wow, log and moles in one. Yeah, Zach, just wait. This is the basics. Just wait. Chemistry is a lot of math. Okay, 7.2, amazing. That's the exact answer, right? And if we think in terms of pH, is that an acid, a base, or a neutral substance? It's neutral, yeah, it's pretty neutral, right? It's a tiny, tiny bit on the base side, but we would consider that to be neutral for the most part. Okay, what about for the second one? What did we get? We were trying to find the POH instead of the pH, which means we have to add an extra subtraction step in there. You got 14. Ten. All right, I also got 10. Let's see, this is what I did. Okay. I did pH plus POH equals 14. Kendrick, relax. So first I found the pH, the negative log of 0.000001, which is 4. So then I just plugged in 4 for the pH, which means you subtract 4 from 14, and you get 10 as the POH. Okay, and then the last one, you probably saw the answer already, but hopefully you got 2. Yeah, right? And again, you're just doing the log of 0.01, and you should get a negative number, and then you're taking the opposite of that. So why do they use logarithms for pH? Right? Because the pH scale is a logarithmic relationship. Uh-oh, you're gonna have to get a new calculator. I see, you're like, oh, I can't do logarithms. I don't know, I can't do chemistry. I'm pretty sure Google does it though. Let's see if you do it like this. It just showed me the answer, but yeah. See, you could type it into Google. Okay. So, right, the pH scale itself is a logarithmic relationship. It's increasing 10 times every time you go up by 1, which means that in order to do this math, right, we can use logarithms to do it, which is why you use logarithms. You don't have to have a special calculator. Any basic calculator should have a log button. If you have like one of those really, really basic ones that's just like plus minus, then it probably doesn't. Even your phone calculator has a logarithm. If you turn it sideways and you get the expanded calculator, there's a log button. But again, you can also just type it into Google and you get the answer. Okay. So, and Google does graphs too. Yeah, Google does everything, which is nice. But it is nice to have a calculator. I would suggest investing in one, especially if you're going to be studying science or math, right? Like I have a TI-84 Plus, which is my favorite calculator. It does everything you could ever want. It graphs, it has log buttons. You can do statistics on it, so it's really great. But it also costs like $100, so it is an investment. But worth it if you're gonna do science and math. Okay, oh yeah, the TI-89 titanium is also a great one. So that's pretty much the end of the session. Hopefully you kind of see how the pH practice went. I will say the assignment that they have you do, yeah, you can graph on a calculator. You can type in the equation and it graphs it for you. Pretty sweet. For some reason, they don't like want you guys to know that. I don't know. All the math stuff that I see in your Canvas lessons is they don't tell you to use a graphing calculator, which is insane to me. Like that was my life in high school, was graphing. Love graphing. Okay. Especially when I don't have to graph. The calculator graphs. The assignment for this lesson is pretty simple and straightforward. So you might even be able to work on it now. But basically, all you're going to do is identify an acid and a base in your house, which we already went through many examples of those. And you're going to include the following in a Google Doc that you turn into me. Chemical properties, physical properties, I guess the difference between those two things, pH, and then examples around you, right? And looking at the chemical and physical properties of acids and bases is what it's referring to here. But if you don't know the difference, I would definitely make sure you know the difference between physical and chemical properties, because they do matter, the difference there. Is it due today? No, right? The due dates are different for everyone, but I think most people, this was due sometime this week, like the 22nd maybe. In fact, hold on, I can check. I just don't want to blow up people's grades. Okay, let's see. Hopefully I didn't miscalculate this. Watch that it was due like last week, and I'm like, oh, okay. So for most people, especially if you started at the beginning of the year, this assignment is not due until April 4th. However, the next assignment for most people is the collaborative project, right? Which I know I've only gotten 2 turned in, and I've gotten 1 person asking me about a topic, meaning that they're working on it, right? And I know a few other people are working on it. Now, the collaborative project is a huge grade. It's 150 points, right? So I want you to spend time on it. The due date for that is a little bit flexible. I'm not going to put zeros in for that until we get another like 3 or 4 weeks in. So if you need more time to work on it, that's fine. Make sure you actually look at it, right? Email me if you don't know what it is, right? Or you need help. There's multiple choices. You could do an experiment. You could do a research paper. You could do a really complicated mixture separation, like a real chemistry one. You could, yeah, that's pretty much the options. Oh, you can also make a lesson that you teach to me. I'm the only person that's going to see it. So if you're shy and you're scared about people seeing you, I'm the only person that's going to see it, so don't worry. And yeah, so there's many options, so make sure that you're working on it. This acids and base assignment is not due until April 4th for most people, right? Some people it might already have been due, or it might be due later than that, depending on when you started the course. But hopefully these notes will help you there for when you get to it. So what I'm going to do next is I'm going to take pictures of the notes and I'm going to put them on the PowerPoint, and I'm going to upload that 2 modules to the very bottom where the virtual session and lab stuff is. And speaking of virtual sessions and labs, let's see when our next thing is. Okay, the rest of the week we don't have anything. Then we have spring break, woo. Then we have another physical science virtual session on April 3rd. Which is the Monday that we come back. Actually, you know what? I think I'm going to move that. I'm going to make it the 17th because we're not going to have moved far enough along yet. So I'm going to be changing that. So April 17th. April 17th, I'm writing it in the chat too. That is when our next virtual session is going to be. Okay. Otherwise, thank you guys for attending. Elizabeth, did you take attendance for me? Okay, awesome. I will talk to you guys soon, right? Email me if you have any questions. There is no exit slip, right? You being here was enough. People who weren't here will have to submit those pH problems to me. But you don't have to. You're welcome to submit them if you want, but I'm not going to require you to. Okay, so I will talk to you guys soon. Bye.